for the invitation. It's been a wonderful conference, and it's Friday after a wonderful dinner, and in a couple of hours, probably many of you will have how many, like 5 times 10, 50 hours in this room, and probably 60 to 70 hours in CIMAT. So I'll keep this. Keep this very explicit, and I deliberately hide all the technicisms. But if you think you need more detail because it's more vague, please feel free and ask. All right. So so let me. So I want to show you the stuff I've been working on, and I think it fits very nicely in this conference because I will tell you something about birational geometry, moduli spaces, and Bridgeland stability. So many things I will just make reference to the courses during this week, and of course I can write formal definitions. So let me start with the goal. Let me start with the stuff I want to show you first, and you let me denote by you the family of smooth hypersurfaces of degree 2 in Pn of degree 2. And well, I claim that if hypersurfaces are of degree 1, those are well understood. And those are basically projective spaces or Grassmannians. So let me go to the next case, which is degree 2, and whatever I will say can be done for a higher codimension of small degree, but let me stick to this particular case. This is already easy enough. I can tell you something. And it's not already non-trivial. So let me consider this family. I claim this family is not compact, and the goal. Let me write it here. Will be to compactify it, and what I understand by that is. I want to construct X projective such that U is contained as an open dense in X. And second, so far this first point is very loose. So I want to impose a second condition, and this is obviously a parameter space. I want hopefully that X to be a parameter space also. Why is this very loose? Because the moment I get a compactification or space X like this, I can always blow up the stuff along the boundary of U, and that could create a lot of spaces that satisfy this property. However, when I impose this second property, this is slightly more restrictive. Something I didn't say, and I'll write it here, is that everything will be done over the complex numbers. All the work will be over the complex numbers. So this is the goal, point 1 and point 2. And of course, the first example, let me write it here, is that I can just remember just remember the coefficients of the hypersurface. So U, of course, sits inside this big Pn where and I can write this as these coefficients as coefficients of quadrics. In other words, you write out an equation of degree 2 and just remember the coefficients and take them all. That, of course, will give you a projective space, and the projective space satisfies these two properties. So I want to mimic more or less this situation. This will be the moral of. So let me construct more spaces. X. So this is what we can. Construction. This is something else we can do. Take U U, and I claim I can embed this into some other projective space by taking Q and sending it to the dual quadric. Well, what's the dual quadric? If you understand this quadric as a symmetric matrix, n by n matrix, the dual quadric will be just the inverse. Easy enough. And of course, this is another projective space, and let me call this other family U star. And this, of course, I'm using that we have the Gauss map that sends Q to the tangent space of Q. Of course, this lies inside the space of tangent of hypersurfaces in Pn. But I can mimic this in other dimensions. So I can, let me write a quick definition. A fixed k-plane, a k-plane is tangent to Q if I restrict the quadric to this subspace and this is singular. Whenever that happens, I declare that k-plane will be tangent to Q. The singularity of this thing can be very bad, but I deliberately don't keep track of that. I just want it to be singular. Well, if I have that, let me write it here. I can have a Chow form which keeps track of these for a fixed Q. I keep track of all the k-planes which are tangent to Q. And that's what I wanted to note here. So these will be delta, so that this is tangent to Q. And this, of course, lies inside the appropriate Grassmannian. Okay? So I'm not doing much now. So let me do an example. So what I'm saying is, if I have Q in P3 smooth of degree, of course, I'm talking this for degree 2. What I'm saying is that the Chow form of this thing will be all the lines in P3 such that this is tangent to Q. And well, one of the properties of these subspaces of the Grassmannian is that I wrote it here. Let me do it with color because I'll use this later. So one of the properties of this subspace is that it defines a divisor, and it is of degree 2. So it is another quadric. So if I start with a quadric, I end up with another quadric, right? Which in the Plucker embedding, this is nothing but the, I'll erase it. So this tells me that this guy lies, I can look at the space of quadrics of the Grassmannian, which of course lies in using the Plucker embedding. The reason I'm going so slow about this is because I'm about to erase the Grassmannian of lines in P3, blah, 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 and just write K and N. But the properties that we see here are still true. So let me even be more explicit about this form. Suppose that, well, this is something that I can associate. This is a quadric in P5, then I can associate to Q. How do I really put my finger on that quadric, on the quadric on P5? Well, suppose that Q is, I write Q as a symmetric matrix. I should be able to write this other quadric, which is going to be another symmetric matrix in terms of the information of Q. And what I claim is that you write this other quadric as the two minors of this matrix. It's not that complicated. And since we know it is a quadric in P5, it needs to be a 6 by 6 matrix, symmetric matrix. Matrix defined by the 2 by 2 minors of Q. So I can make this, I can write this quadric very, very explicitly. So after these notations, you probably don't object, or maybe you do, but I will write this from now on as the second wedge of Q. Okay? So, by the way, this in classical literature is this is the famous line, quadric. This is the quadric line complex. Towards the end of Griffiths and Harris, you can find all about this complex. So, so what I've done here is, by the way, questions? No? So what I've done here is I have defined for you, generalizing this, a series of maps from U into the appropriate linear system that sends Q to the K wedge of Q. Okay? And I claim this guy is injective. This is a linear algebra. This is a linear algebra expression. If you have two matrices whose K minors coincide, what can you tell me about the original matrices? Well, to prove that they are multiple of one another. So, and this will be true for K all the way to K sub n. So, so the image of this U in here is going to be injective, and then I can take the closure. And all those spaces will satisfy with these two properties. So I have constructed for you many different compactifications of the same space U. So let me take them all and define a single space, whose birational geometry is the one I want to analyze now. So this will be definition. How do I want to start this? This is basically Schubert in 1879. In the same paper in which he defines the Schubert calculus, you can find this definition for these quadrics. So basically, you take U and embed it into Pn, and all these linear systems, by taking Q, and you send it to Q, the first wedge of Q, the second wedge of Q, all the way to n minus wedge of Q, which is nothing but Q inverse. This map is injective because all these single maps are injective, and now you can take the closure. And what that means is that you're somehow capturing all the information that each of these closures is giving you. So X, which is defined as pi, the closure of U is called the space of complete quadrics. And if you want to make emphasis which kind of quadrics, I'll write in Pn. So let me, okay. So far, what I've done is take the family of smooth quadrics, and I've defined for you a very large space, this very large compact space, which is this X. And if you see, it is more or less clear. Probably you need to do a little bit of work, but it is more or less clear that you have morphisms from X into the factors, into all these factors. And there will be exceptional loci for all those morphisms. And let me do an example first. N equal 1 is, n equal 1 is not interesting. N equals 2. This is, take C, and you only have two factors in P5 cross P5 dual. And of course, you have maps towards P5 and P5 dual. And I am still in the range of these 2 points. These 3 spaces satisfy these two points. So I haven't done, and just to emphasize that, this satisfies 1 and satisfies 2. Okay? And now what I want to do is, let me replace this by making reference to Paolo's lecture. Is I want to understand the directed graph above X when X is the complete quadric space. Okay, directed graph for below X, where X is complete quadrics. For instance, for this particular case, I only have two spaces, and I know a little bit more. If you label these maps, I know that the exceptional locus is of EI is pi I, and let's define this divisor H sub I just by pulling back the hyperplane class from the appropriate, in this case, from P5 or P5 dual. Okay. And if I want to make sense of this directed graph and see how many models I have behind this space, which are birational, I can analyze the effective cone of this space. And for this particular case, it's very easy. The effective cone of X, I can draw it like this, where this is E1, this is E2, this is H2, and this is H1. And this guy right here is going to be the ample cone. So I have the birational models coming from X, coming from the ample cone, which is X itself. And what I'm saying is that I get one model for each of the NEF divisors. And these are these two spaces. Okay? So, so in order to analyze this in higher dimensions, which is what I want to tell you, I first need to know something about these cones. So okay. So let me write a result. So a proposition of a theorem, if you will. Say X complete quadrics in Pn, and the effective cone of this guy will be generated by the exceptional divisors, which I didn't tell you what those are. But you can imagine that in the general case, you will have several factors, and you can project. You can just forget one of the factors, and you will get a morphism towards that projection. The exceptional locus of that, if you forget the first factor, is E1. You can forget the second factor. The exceptional locus of that morphism will be E2, all the way until n. And if you project all the way into each of the factors, say the first factor, you pull back the hyperplane class, and that will be H1. This is different notation for a projective space. You pull back the hyperplane class here, and that will be H2, and all the way until the n. And those divisors generate the cones we are interested in. And the corollary of this is that X is Fano. What that means is that the canonical class of X, which I can compute, well, minus the canonical class, is to H1, H plus H2, Hn to 1 plus 2, H ample, is ample. Okay? So, so we know, at least, from this computation, that this X is Mori dream space, and what that means is that it will have finitely many models. So we know from this computation that I want to understand the directed graph, and I already know. So this will tell me that there are finitely many. Because this variety is Fano, and it would make sense to know which models are those. So let me show you the next dimensional case. Let me see. So let me do n equals 3. And all what I'm about to say, you can find it in a couple of papers by Semple back in the 50s. It's, I think the name is complete surfaces 1 and complete quadric surfaces 1, complete quadric surfaces 2. By Semple is classical. So in the next case, I have X complete quadric surfaces. This is in P3. Of course, we have the usual compactification. It is a projective space, and just by definition, let me write it here. By definition, this guy lies inside P9, P20, and P9 dual. So I have a morphism towards a variety, which I'm not telling you what it is, but is by forgetting the first factor. 20, 20, 20 dual, and the symmetric. Oops, P9, and then all the way to P20. I know that I have all those morphisms, and it just so happens that the exceptional, well, what that theorem is telling us is that the exceptional locus of this first map is E1, the exceptional locus of this is E2, and the exceptional locus of this map is E3. They generate the effective cone. And the H's, the H1 is the pullback of the hyperplane class, H2 and H3. Okay? So far this defines the birational geometry coming from the Neff cone. So what happens if I try to draw the Mori chamber decomposition of the effective cone so that I know how many birational models are there? This is what I want to do here. So this is theorem, well, it's part of the same result. The stable base locus decomposition of F is the following. So I have a cross section of the effective cone that looks like this, right? It's a cone, and then I draw a cross section. I will see some, roughly speaking, something of this type. And then the ample cone should be sitting like this. Well, it's not that it should be. It is sitting like this. The ample part, if this is the ample part. And now I'm supposed to write a decomposition of the rest of the cone that will tell me something about the other models of x. And the decomposition looks like the following. Let me call this intersection number P. So what I'm saying is that the Mori-Chamber decomposition looks more or less like that. And where the movable cone of x is exactly this part. H2, H3, H1. And what that means is that there must be a flip here. There is a unique flip, which in this diagram, I should draw like, there is another map here towards something I will call C, and something. And if you see this triangle that looks more or less like this is the ample cone of x plus. And it will have, again, contractions going from divisors towards the boundary of that cone. So here I have more maps. Here it is. So I have 4 minutes. Let me tell you how do I define this x plus. The x plus, so if you see, for this definition, I'm taking into account all the planes that are tangent to Q. Now what I will do is I will take into account all the lines that are contained in Q. So in other words, Q more or less look like this. And this is a ruled surface. So what I can do is I can forget about the surface and just remember the ruling. So in more formal terms, this is take Q and consider the Fano scheme of lines containing Q inside the appropriate Grassmannian. And this x plus will be, by the way, this is a pair of conics. Okay? And this x plus will be the Hilbert scheme of those conics in the Grassmannian, morally speaking. So what I've been trying to do, so what I've done is that now x plus is another space that looks like this. It's a compactification for U, and again, it satisfies the second condition. That's why I had to went through the explicit construction of this parameter space. Okay? Now, I have 3 minutes. That's, by the way, just n equals 3. I can play this same game in higher dimensions because I have a result of Segre that says that Q is determined by the Fano of lines that it contains. So this association will always go through. So now let me switch gears in the next 1 minute and tell you something about curves in P3. I will just use this part of the board. So this is joint work with Gallardo and Schmidt. So say that I have E, let me take white chalk. E in P3, an elliptic quartic, elliptic curve. This elliptic curve is the intersection of two quadrics in P3, right? And now the game I want to play is that I know many, many different degenerations for that quadric. And what I want to do is, okay, if I know how many degenerations, can I tell you something about the degenerations of the curves it contains? That's roughly speaking the game. So if you consider the Hilbert scheme, what we can prove, let me write it here, is that the principal component of the Hilbert scheme of those curves, and by principal component I mean this, is two blob of of the Grassmannian of lines in P9. And where is this line coming from? Well, E is the intersection of two quadrics, so this determines a pencil. And this as an element of this Grassmannian. And what I'm saying is, as long as E is smooth, well, something I'm not saying, but it's true. As long as E is smooth, you can look at the family of smooth curves inside this Grassmannian. But when you consider the closure in the Hilbert scheme, you have to blow up that Grassmannian twice. And this resembles very much this picture. That you blow up P9 in order to get X, you blow up P9 twice again. So let me just write over time how we can understand this as some moduli space of stable sheaves with the following Chern character: 4 minus 8. And because we can do this, this is part of the theorem. Now we can vary the stability condition, just in the same way Macquarie did it yesterday. So let me draw how a slice of the stability condition looks like in terms of this beta alpha. This should be alpha, and this should be beta. It looks more or less like this. And probably you recognize this. Well, it depends on my gradient, but. And what I'm saying is that the Hilbert scheme is here, the Hertz blob is here, the Grassmannian is here, and here's the empty set. And these resembles, or at least should resemble something to the case of quadrics. It's coming from this geometry. And sorry, I went over time. This is all I had to say.